Somewhere in a lab there is a glass of water. Inside it, a single bubble smaller than a grain of salt. Hit it with sound. Just sound. And it flashes. For less than a billionth of a second, the inside of that bubble becomes hotter than the surface of the sun. We have known about this since 1934. We still cannot explain it. The effect was found by accident. In 1934, two physicists in Cologne were working on sonar. They lowered ultrasound generators into a tank of water and noticed a faint fogging on their photographic plates. The water was producing light. They called it sonoluminescence, sound turning into light. For 50 years it stayed a curiosity. The problem was the bubbles. Ultrasound in water creates a chaotic cloud of them. Thousands, all collapsing at slightly different moments. You could see the glow. You could not study it. Then in 1989, Philippe Gaitan and Lawrence Crum managed something remarkable. They trapped one single bubble in a standing sound wave and held it there, suspended in the middle of the water, pulsing thousands of times every second, and with every pulse it flashed. Here is what happens. A sound wave is a pressure wave. When the pressure drops, the bubble expands up to 10 times its resting size. Then the pressure swings back and the bubble is crushed. It does not deflate. It implodes. The wall of the bubble rushes inward faster than the speed of sound in water. In less than a microsecond, a bubble a few micrometers across is squeezed down to almost nothing. Everything inside is compressed with it. The gas has nowhere to go, so it heats. Estimates for the peak temperature range from 10,000 to 25,000 Kelvin. The surface of the sun sits at about 5,800, and at the very bottom of the collapse, the bubble emits a flash of light, lasting less than a nanosecond. This is the part that bothers physicists. The sound going in is gentle, a pressure swing of roughly 1 atmosphere, the kind of energy a loudspeaker produces. The energy coming out is concentrated by a factor of about 1 trillion. Almost nothing in everyday physics focuses energy like that. So how does it work? There is no agreed answer. One family of theories says it is simply heat. The gas becomes so hot that it glows like a very small star. Another points to Bremsstrahlung, the light emitted when free electrons are deflected inside an ionized gas. Others propose shock waves within the bubble or effects borrowed from quantum field theory. Each explains part of the data. None explains all of it. One detail makes it harder. The effect is far brighter when the bubble contains a noble gas, such as argon. Argon is chemically inert. It reacts with almost nothing. Any theory built on chemistry has to explain why the least reactive gases give the brightest light. In 2002, a group announced they had gone further and achieved nuclear fusion inside collapsing bubbles. If true, it would have been enormous. Other laboratories could not reproduce it. The claim fell apart, and it left the field cautious about extraordinary temperatures. So this is where we stand. 90 years after the discovery and more than 30 years after we learned to trap a single bubble, we can create the effect on a desk. We can film it. We can measure it. And we still do not fully know why a bubble of gas, squeezed by sound, decides to emit light. Which is, in a way, the best kind of physics, not a mystery in a distant galaxy, one sitting in a glass of water.